Welcome back to ECE 320A. This is our last time to meet to discuss material. The next time we see each other, you will be prepared to take the final exam, which is Friday. That's the plan. Make sure you get plenty of sleep, you're hydrated, and you're well fed. And you can be well fed by maybe having some pancakes, right? With some Butterworth syrup so that you're doing the Butterworth filter design while you're eating breakfast. Process for the final hasn't changed since we saw each other a few hours ago. You should be familiar with that. These notes hopefully will be posted soon after we finish today, which is maybe in a couple of minutes. Thank you for your attendance. No, maybe we'll spend a little bit more time than 2 minutes talking about material. But the topics are chapters 10 through 15. If you see on the practice final a problem dealing with 2 ports, I will replace that with something else. So most of the other topics should be addressed on that final, and it is multiple choice. Be ready for that, but do show your work. It may be important to get some partial credit. Because you always say you don't want to show your work. The question was, why are you looking at me? If you show your work, hopefully it will get you more points than not showing your work. That's the idea, and you'll need to have some work to answer the problems. Based on feedback, you want to do more than what's shown here when I'm asking you a balanced 3-phase power problem or question. You want to give me more than just a blank piece of paper. Let's say that we now have a balanced 3-phase source. And it's delivering power to the following loads. Suppose that you now have load 1, which is 24 kilowatts at 0.6 lagging power factor. Load number 2 is 10 kilowatts at a unity power factor. Load number 3, 12 kVA at 0.8 leading power factor. Load number 4, no, I'm teasing. We'll stop with 3. How's that? What does unit mean? What is a unit? 1. So now we have unity, or a power factor of 1 in load number 2, where we have a power factor of 0.6 in the load 1. And why do I not say leading or lagging in the second load? It doesn't matter, does it? If I have a power factor of 1, what does that really tell me? If I have a unity power factor, how is the power partitioned? The reactive power is 0. You do not have a reactive component. The cosine of theta is 1. These power factors give you the angle associated with the loads. And in this particular, if it's talking 3-phase, what do you know about 24 kilowatts? It's split among all 3 phases. I haven't told you an A phase, a B phase, or a C phase, and I also haven't told you how these are interconnected, have I? I haven't said Y or delta, and you really don't even need to know that necessarily, depending on what you were asked. So, all I've said is we have a balanced 3-phase source. and you have 3 loads with these particular properties, what can you tell me about what is given in terms of information? Or maybe what I should say, well, let me just ask the question first. So let's say that we have some additional information. Somebody tells you that the line voltage at the loads is 208 volts RMS at 60 hertz. That tells you where you are located. Now you know you're in North America if it's 60 hertz, if that's important. Maybe there's some extra credit on the final. If they say 60 hertz, you go, oh, we're in North America in terms of this power system. And I might give you a point just because you realize that. If it was 50 hertz, where would you be? Europe. Just trivia, okay? Or current event. Now, the question is, find the line current that's supplying those 3 loads and the combined power factor of the loads. So this may be a little bit more problem than what you will get on the final. This could represent maybe a half an hour of work if you wanted to do this. So this is maybe more involved than what you will see, but this helps capture some of the concepts dealing with 3-phase power, sinusoidal steady-state power, etc. So this is a good review, is why I'm doing it this way. Now, given this information, what do you already know about what's stated relative to load number 1? And here you have to be very careful with the units. That's what you want to be aware of when you're talking about complex power. Complex power, in general, if I just say something like complex power, you should be thinking S, where S is a complex number or a complex quantity, which could be a real part and a reactive part. And this could be written in terms of its magnitude and angle. And so this is now real power. This is reactive power. This, obviously, the S is the complex power, but this part here, just the magnitude, we give that another name. Do you remember what we call that? Apparent power. Now, going back to our problem, that was just good information to know. But returning to our problem, what can you tell me just by looking at load number 1? If somebody said in an interview, oh, you have a load that's absorbing 24 kilowatts at a lagging power factor of 0.6, what could you just quickly tell them? What kind of power are they referring to, or did they give you? And this is where the units come in. Watts mean real power or average power. Real power and average power are the same. This is now saying there's the real power, and that's the horizontal component in this complex power triangle. The apparent power is the length of the hypotenuse. The real power is the horizontal component. The reactive power is the vertical component. What did we give, or what were we given? Well, I can say that you know even more about load 1. What do you know about the angle of that? Do you have a reactive piece in load 1? Yes, because you have a power factor. So you do have a vertical or a reactive component. And in what direction is Q, the reactive piece, is it positive or negative? So from this, you have a theta. Is it positive or negative? It's positive, which says Q is positive. Without solving or calculating anything, you know the length of your horizontal line in this complex power triangle. This now represents all 3 phases, so this would give you the full complex power in load 1. If you just needed to know one phase, since it's balanced, you now know that 24 divided by 3, or 8 kilowatts, is the real part in one of the phases, A phase, B phase, or C phase, if somebody asks you that. What about load 2? Without calculating anything, what do you know about 10 kilowatts? Which piece of the triangle is that? That's just like in load 1, that must be real. What do you know about theta? It's 0 degrees. So there's no reactive component for load 2. What about load 3? Now this is volt amperes. All of our powers are volt amperes, but we use units of volt amperes specifically for what power? The magnitude of the complex, or that's the length of our hypotenuse, isn't it? So this is the magnitude of S, and that's what we're calling the apparent power. That's now the magnitude of S sub 3, or that's the magnitude of the complex power for load 3. Let's now find all the different pieces, our triangles, for each of these loads. Load 1, load 2, and load 3. Let's get into a solution mode. S1. Uh-oh, now you're going to hold me to my colors, aren't you? Was real power blue, reactive power was green, and the complex power was red, I believe. I hope I'm not messing that up, but you'll be able to make the translation if I'm doing it wrong. And if you have 64 crayons, you can make them whatever color you want, right? Am I correct? Okay, so blue is horizontal, green is vertical, and red is hypotenuse. Oh, gosh. Yeah, I'm not getting a different room, but I just jammed my knee into the desk. So now I'm going to have to shake it off. Okay, yeah, and I wasn't even shaking, was I? This desk didn't move. It's pretty solid. Well, it shakes, I guess. All right, so what do we know? We know the blue piece. If we are going horizontal, that's now 24K. And remember, this makes up all 3 of the phases. We may or may not need to pull them out. But if we do it all at once, then we'll get the correct angle. All phases have the same angle because we're dealing with balance. They're just 120 degrees apart. So we're finding the fundamental angle of this S1, or the relationship between the voltage and current, or the angle of the impedance for this complex power. Here's 24. Now what can we find? We were given the power factor, weren't we? And the power factor is the cosine of theta sub 1. And we were told that that was 0.6, and I've set this up so that 0.6 is 6 over 10, or 3/5. Now I know my horizontal distance is 3 and my hypotenuse is 5. Now I have a 3, 4, 5 triangle if I'm using the trig, if I want to. So now I know that if this corresponds to 3, now I'm going, or you could, if you wanted to, solve this for theta 1. You're now saying the inverse cosine of 0.6, but that's this 53.1 degrees. And now if you go up at 53.1 degrees, that's what this angle represents. This distance is the 5 on my 3, 4, 5 triangle, which means that, or we could even calculate it if you don't have to remember your trig, you can just plug these in, so that now you have power factor 1 is also P1 over the hypotenuse, or the apparent power. And this was 3/5. So that now the apparent power, S1, we have some shaking going on, don't we? Some serious, we need to filter that out. So maybe we'll build a high-pass filter and get rid of that low-frequency rumble. It's making me nervous and shaking. Actually, it's just vibrating the floor and I'm shaking. Sorry. You wanted to study for the final. Let's get back to that. S1 is what? S1 is now P1 divided by 3/5, or 8 times 5, K, which is now 40K, and that's in volt amperes. We now know what this hypotenuse is. That's 40 kVA. And we can now connect those lines to obtain our reactive piece. This piece is now proportional to 4 in this 3, 4, 5 triangle, so that now we could just remember our formulas. We know that Q1 is now the magnitude of S1 times the sine of theta 1, where theta 1 was 53.1, but we know the sine is opposite over hypotenuse, which is 4/5. We now have 40K times 4/5, or 8 times 4K, or 32,000 VARs. And we can now label this one Q sub 1. Again, this represents all phases of Q1, A, B, and C phase. This is now 32 kilovars. And there's P1. Questions on S1? S1 is actually a complex number, isn't it? In general. Questions on that? Actually, what are we trying to, well, let's not get ahead of ourselves, but we are really trying to sum up all 3 of these powers, and we need to do that algebraically with the components real, and reactive of all three loads. Once we have the total power absorbed by our loads with the line voltage, we will be able to calculate the line current. We'll get there in a minute. But what do we know about the second load? That one's really hard to calculate, isn't it? No. That's just one piece. That's the real part. And that's now 10K plus J0 volt amperes. What's S3? Or how are we going to find S3? Now what are we given? Now we're given the hypotenuse and we have an angle. Which direction is the angle? Oh, I didn't finish that, did I? To be consistent, this now says theta is what? It's now negative, which says that Q is less than 0. It's going vertically down. We now know the hypotenuse, that's 12K, so we can say that we have, well, we have this, and we know cosine of theta sub 3 is 0.8 or 4/5. Now we again have this 3, 4, 5 triangle. Except, what do we know about the angle here? It's not as big, and I've drawn it maybe bigger. Because the cosine of that angle needs to be 0.8 instead of 0.6. So in this case, we know that the magnitude of S sub 3 was given to us to be 12 kVA. What's P1, formula-wise? That's S1 cosine, whoops, this is 3, sorry. Wake me up. This is P sub 3, this is S sub 3 cosine of 3, theta sub 3. This is now 12K times 4/5, or that ends up being, if I've done the math right, 9,600 watts. And Q3 is the apparent power times the sine of theta sub 3. This is now 12K. Sine is now 3/5. So that this now becomes 7,200 VARs. Yes? So now where's the leading part? I should have put that in. This is now minus, minus, and minus. Actually, I don't need to do that if theta. What I should have done is say that this is now, let's say, a minus 3/5. We would solve for theta sub 3, and I didn't do that, but what is this? Is this 37? 36.7, so this is minus 36.8 degrees or something like that. 36 point, if we did the inverse cosine of 4/5, and since it's leading, we know it's a negative angle. So we assign that negative because it's leading. Okay? The question was, where do we get, or what do we do with the sign? Now Q3 is negative because it's a leading power factor. And if we sketched that, we would have a real part of 96, a reactive part of 72, and our complex power is now there. Questions on that? Now what we want is the total complex power of all three loads, all three phases. We have all three loads. The beauty of complex power is we can just add up these vectorially, can't we? Or algebraically. We can say this is S1 plus S2 plus S sub 3. And without going through that, we add up all of the P's and add up all the Q's vectorially. We end up with 43,600 plus J, 24,800 volt amperes. Yes? So now what was I doing? Here I was working off the question was, where did this minus sign come from, I think, or why didn't I put it in the 4/5? So now what is actually negative? We had a leading power factor. That tells us our angle is negative. If I take the cosine of minus 37, how does that compare to the cosine of plus 37? It's the same. Cosine's even. So the 4/5 is the cosine of theta sub 3, and that's now this 4/5. This 4/5 is the cosine of theta sub 3. This is the sine of theta sub 3, but this was the sine of minus 36.8 degrees, and that's why we get a minus 0.6. And that's directed down then in our triangle. And now we add the 72, or we subtract 7,200 from load 1, which was 32,000, and that better give us 24,800. We add all of the P's. We add 9,600, 10,000, and 24,000 to obtain 43,600. That's our total power for all three loads, all three phases. Now what? We were supposed to find the line current. Yes, question? Why is the angle negative? It's because of leading. So now when we have a lagging power factor, the question was, why is that angle negative in load 3? It's the difference between leading and lagging in our problem statement. So if we know we have lagging, what kind of a load is that? Is it inductive or capacitive if we have a lagging power factor? Is it more like an inductor or a capacitor? It's an inductive load, isn't it? It's an inductive load if it's lagging. It's a capacitive load if it's leading. Most of our loads, industrial loads, might be more inductive, and we may have to introduce capacitor banks or capacitors to try to take out some of that inductive power. We're trying to reduce this angle. Ideally, we would have that angle equal to 0. Then we would just be demanding from the power company power that we are physically using. If that hypotenuse gets a little bit bigger or longer than the real part, then the apparent power that we're apparently asking the power company to supply us with is larger than we're actually using. And they're going to charge us for making them deliver more power than we are actually absorbing or using. Yes? So the lagging and leading is with respect to the current. So the current is lagging the voltage in an inductive load. So now just think of what you have relative to, you could just use Eli again. You could say V is equal to Zi, and Z is J omega L. That's giving you a 90-degree, basically, addition to I to get what V is. So the current in a pure inductive load is 90 degrees behind the voltage. In a capacitor, you have the 1 over j omega c, and now you have a minus 90 associated with that impedance. And that's your negative angle for a capacitive load. We are being asked to find, we are given the line voltage, and we're asked to find the line current. What do we sort of know? I would maybe, if it's not real clear, I would just draw a sketch. I didn't tell you how this is connected, did I? Whether it was Y or delta. You can just assume one. So I would just assume, since they're asking for the line current, I would say let's just assume that this is Y connected, meaning now we have something here, and there's, let's say this is A, this is B, and this is C. We have another load that's here, and it has its B and C, and we have, if we were in another art class, you might think we were drawing cartoons, but this is now A1, B1, C1, those are stick figures, but this is now the A phase of my load that I'm drawing. Let's say this is the B line. There's another B line for 2. Here's B3, A2. What were we given? We were given the line voltage. We were given that voltage between the A phase line, or the A terminal, and the B terminal on our load was 208. And we know the magnitude between B and C is 208, and between C and A is 208, because it's balanced. What we were asked to find is the magnitude of this current, I sub L. You've told me that for a single phase, what's the expression for complex power? S star is VI star, and the units on these, we've now converted our voltages. If I give you a time domain waveform, by convention, the amplitude on that time domain waveform is a maximum value. Then if you do the RMS of that sinusoidal voltage, you would be cutting that by this square root of 2 to get the RMS magnitude. So I could give you time domain waveforms and ask you to start calculating powers, and you need to make sure that you're keeping track of the kinds of magnitudes or amplitudes that you're playing with. We now have a three-phase system. Do you remember if I had a single phase complex power, how could I find the total power in a balanced system? So now if I know that the complex power in one phase of my load is, let's say, S sub phi bar, this is complex power in a phase maybe I should say in a single phase of the load. That could be the A phase, the B phase, or the C phase. How do I get the total power if it's balanced? Total power, it's all three phases, isn't it? So that's one way of finding, but we really don't have, we are starting actually with this. We've now computed up above, we now have S sub t. That's this, whatever it was, 43,600 plus J 24,800 volt amperes. That was 3 loads with all 3 phases. Do you remember a formula for total power when you are given maybe, what are we looking? We're looking for the line current. This in blue. We know the red line voltage. From this expression, you could find the angle of that complex power. Yes? That's now the inverse tangent of 24,800 over 43,600. But the total power formula, one way to do that, or do you remember this? If I just said the average, total average power, square root of 3, V line, I line, cosine of theta. Do you remember that? And Q sub t is square root of 3, V line, I line, sine of theta. You know PT, you know V sub L. We can compute theta. We could then solve for I line. Or we can combine all of these into ST. This is just PT plus JQT, which is now the square root of 3, V line, I line, cosine theta plus J sine theta. And that in parentheses should just make you feel warm and fuzzy. Who is that? Euler. So you now know that S total is this square root of 3 V line, I line, e to the j theta. Or a lot of times we just say square root of 3 V line, I line, and I'm not overbarring V line and I line. Those are just magnitudes. And we could represent e to the j theta by just saying, oh, angle theta is sort of our shorthand. And if it's in this form, that's like a polar form of this complex number. We could say that's equivalent to where we are calling this the angle of S sub t. Now, comparing the two pieces, we have a magnitude piece and an angle piece on the right. We have a magnitude piece and an angle piece on the left. We can now find the magnitude or the hypotenuse of this, 43,600 plus J24, or we could find the angle, either of those, to find I sub L. If we now use this being the square root of 3 V line, I line, I'm saying this is S sub t, this is theta sub t, which we haven't yet found, but we know the horizontal piece is 43,600 watts. We know the vertical piece is up because it was positive, and it was J 24,800 VARs. And we could then say that the power factor total is what? This is the power factor of all three loads combined. That's the cosine of that angle up there, theta sub t, which is 43,600 over the magnitude, or over the hypotenuse. And I'm hoping that my calculation is correct. I calculated that to be 50,160. Just taking the square root of 43,6 squared plus 24,8 squared, giving me 50 for a value. This is our real power. This is the apparent power. Now, if your calculator died, you could just write that ratio. You might have had a hard time finding the 50,000, but irrespective of that, you now have the magnitude of S sub t. What could you tell me about power factor? What do you have to tell me about a power factor? Pardon? Leading or lagging and the numerical value. You need two pieces to the power factor. What piece can you immediately tell me relative from seeing this triangle or from seeing that ratio? It's lagging, isn't it? The Q is positive. And if you compute that ratio, you end up with a power factor total being 0.869 lagging. And now that we've found the magnitude of our apparent power, we can say that I sub L from this relationship right here is that apparent power divided by the square root of 3 divided by V sub L. And that's I sub L. I sub L is now the apparent power divided by the square root of 3 times V sub L. That's this 50,160 divided by the square root of 3, 208, and that ends up being 139.2 amps. Is that a safe amperage? No. Okay, if you want, you would probably hear that. It would be buzzing. Okay? You would stay away from that very far. Okay? Even if you divided that by 100, it's still not safe. 1 amp is very dangerous. 100 milliamps is not good. You can't even let go of 100 milliamps. 0.1 amp. Yes? You didn't like my story? Go ahead.
No, you're getting off track. So, what's the difference between using the power total, the real power total, like versus using the...
So the question was, which of these formulas, or why did I use the formula that I used? It really doesn't matter for the information that I was trying to extract. If we used, so the question was, why didn't I use this P sub t formula, or why did I use the S sub t formula? You could have used either one, and they better give you the same value. In the average power, this was the 43,600. We could divide that by the square root of 3, V sub L, and the cosine of theta. You would still have to find that angle, theta, or the cosine of that angle, to obtain I sub L. And if you did, you should find that that equals this 139, if that's what it was, 139 amps. And that 139 amps is an RMS quantity. So it didn't matter. I was just maybe doing, it's really however it comes to you.
So for the current total, you only use the magnitude, right? You don't use
So in this particular, so what we were using, how much of this expression do we need? I think is what the question was, maybe. We now, in this formula for the total complex power, we've written it in polar form. So we have two pieces, a magnitude piece and an angle piece. And we decided to just use the magnitude piece. But you could have found the angle. We were not, in what we computed, we really never had to find the angle explicitly, did we? So we avoided that. We just had to use our Pythagorean theorem. We had to look at the real part, or the horizontal part, square that, add that to the square of the reactive piece, and take the square root to obtain 50,160. So once we had the apparent power, we said, let's just play with that. Let's not even worry about the angle. We could take the ratio of P to the apparent power to obtain the numerical value for our power factor, and since we had a positive Q, we knew that it was lagging. Then we said, oh, this was good. Let's just go back to our polar form for the total complex power and just use the magnitude piece to find I sub L. And that was okay. That answer your question? Now, what else could we ask? That basically finishes that question, but I could start asking more. I could ask, what's the voltage at the generator terminals? I gave you the voltage at the load terminals. When would those be the same? If our transmission line didn't have any impedance. If our transmission line did not have any impedance, then our load at the load terminal, the voltage at the load terminals would be identical to the voltage at the source terminals. Suppose that was not the case. Suppose that you now are told that you have 0.05 and J 0.02. Let's say that this is now in, so that this would be the A phase at the load. We didn't calculate that, but what do we know is true if somebody said, what's the complex power of the transmission line in one of the phases? Could you find that with what we've found so far? You just determined this line current magnitude to be I sub AA. This is now A, and this is, let's say, little n. We found this to be 139 amps. How would you find the complex power absorbed by the transmission line? And this would be just one phase. Bless you. How would we find that? What's a formula for the complex power that we could fairly quickly use? Or if you've forgotten, you could say, well, I know that this is VI star in phasors, but V is just ZI times I star, but I times its conjugate is the magnitude squared, so this is now Z magnitude squared, and that's what we actually have. Meaning this is now I sub AA, and we have that, so that if we needed it, we could find the complex power of one phase of the transmission line is now this 0.05 plus J 0.02 times 139 squared. If you needed the voltage, well, then you could back out V sub AN from, because you were given capital V sub capital A, capital B, weren't you, in terms of its amplitude or magnitude. And you could find all of those other relationships if you wanted to by the three-phase relationships, meaning if I wanted V sub AB, how is that related to, or maybe if you were given this at the terminals of the load. That you were told was 208. What if you wanted V sub AN? You would either have to say, or if you have to know more than just the magnitude, if you needed V sub AN completely, you would need to know the phase sequence, whether it was positive or negative. If you said that you now have an ABC, or a positive phase sequence, this now tells you that V sub AB is equal to the square root of 3 at 30 degrees V sub AN. Do you remember that? And if you just needed amplitudes, once you had, and what were we given? We were given V sub AB's amplitude. If you just needed to know V sub AN's amplitude, you could get that by dividing V sub AB by the square root of 3. Questions on that? So there's a lot of different relationships that you need to remind yourself or refresh yourself on relative to three-phase. When it's single-phase, then you're just dealing with V bar, I bar star. Questions? We haven't gained any time on our clock. It's still 8:28. So we can continue to go to 8:28. Eek. Whatever time it is. Do you want to start a Bodie plot? We okay with, yes? So V sub AN is considered a phase voltage under what conditions? So it depends on how the load is connected, doesn't it? If the load was a Y-connected load, then V sub AN would be a Y voltage. I'm sorry, would be a phase voltage. It may not even exist if your load was delta connected. Then you would just have your phase voltage would actually be V sub capital A, capital B. And then you'd have to remember what your phase current is, and that's different than your line current in a delta connected load. Other questions? Let's look at a Bode plot where we have a complex factor. And that's 25 times S over S plus 0.5. Now you could plug that into the quadratic formula and find your roots. If we just started completing the square, we would need an S plus 2 squared to give us the S squared plus 4S. Then we have 4 coming out of that as the constant, but we need something to add to that to get to 100, and that's 96. So what's left is plus 96. And if we wanted to write that, so this is now S squared plus 4S plus 4 plus 96. There's where the 100 is. So that if we wrote that, this now needs to be a little bit less than 10 squared. But we don't need to worry about computing complex factors as complex factors. What did we agree we could do in this class? We are going to approximate those as two reals that are right on top of each other. So we want to now that we see that that's a complex factor, we want to approximate that as two reals. So we're starting with an S squared plus 4S plus 100. We are saying, let's just agree that this is the square of the distance away from the origin. That's our natural frequency squared. So that now our natural frequency is 10. What we started with, or were given, was we were over here at minus 2, and up here a little bit less than 10 in terms of a pole. We are agreeing to do what? This distance is 10. We're saying you can just go ahead and move that all the way around at a radius of 10. And approximate these two poles that are at minus 2 plus and minus j, a little bit less than 10, by two real poles at minus 10. That's what we're assuming. Meaning we are allowing for this S squared plus 4S plus 100 to be approximated as S plus 10, quantity squared. And if we multiplied that out, we would have an S squared plus 20S plus 100, and this is our error in approximation. We're changing 4 to 20, and we're okay with that. It's not correct, but this allows us to more quickly sketch these Bode plots, especially when, and that's about as bad as we are going to get with the approximation, because look at where we started. We almost were purely imaginary with our poles. They were almost on the imaginary axis, and we slid them all the way around to look real in our approximation instead of leaving them as purely imaginary or very close to imaginary. So this would be a very gross approximation, but we're okay with that, which means that instead of sketching the Bode plot of the original h of s, now we have this new h of s, which is 25s over s plus 0.5 times s plus 10 quantity squared. And what do we need to do now to sketch this? Now you should be ready to run with sketching this. What form is this in? Pole zero form, and we need it in time constant form. If we place this now in time constant form, we don't need to change the numerator yet. We factor out a 1/2 from the first term. And if you don't see how to factor out that second one, just write it as 2 linear factors, an s plus 10 and an s plus 10. Then it's easy to see that a 10 comes right out of both of those. We have a 10 s over 10 plus 1, and we have that again. Or we have, what, 25 divided by 1/2 is 50, divided by 100 is 1/2, so that we end up with 0.5 s over 0.5 plus 1 and s over 10 plus 1 squared. Is it clear what you need to do now? And we could just start writing down this in terms of sentences or words. We could describe each of these different factors in words. What's the contribution due to the, so how many pieces do we have? We have a constant piece. We have a 0. Where is that 0? It's at the origin, isn't it? So that's a special 0. We have a real pole at 0.5, and we have 2 real poles at 10. We could say, okay, let's look at the constant. And our magnitudes, we're wanting those in dB so that we can add those up. This is now 20 times the log of 0.5. What's 20 log of 1? 0. So now we're logging something less than 1. What would you expect? A negative dB. So this is now 20 log of 1/2 is another way of looking at that, so that this now becomes 20 times the log of 1 minus the log of 2. And there's the log of 2 again. And I told you to remember that, did I not? That's 0.3. This is 0. So now we have 20 times, or minus 20 times 0.3, or 2 times 0.3 times 10. I'm basically trying to get 6. So I now have minus 6 dB, and that's true for all frequencies. That's what the gain contributes, or the constant contributes in that transfer function. Questions on that? So now you just draw a straight line at minus 6 dB for all frequencies. No slope, it's flat. The constant is knocking our gain by 6 dB. What's the phase? Due to the constant. What's the sign on 1/2? What's the sign of 0.5? That was positive, so our angle, or phase, what's the angle of 0 degrees? I'm sorry, what's the angle of a constant that's real or positive? 0. It's getting late. See, it's 8:28. So this is now 0 degrees for all omega. And you don't have to really even worry about how that impacts your phase curve, total phase curve. What about the 0 at the origin? What's its magnitude doing? When you have something at the origin, what happens? It's always sloping, isn't it? And now you have to remind yourself, is it sloping up or is it sloping down? Zeros are in the numerator, which are upstairs, so we have a positive slope, and there's only one of those. It's sloping at 20 dB per decade for all frequencies. Where do we pin it? So now this is a slope of plus 20 dB per decade, or if you needed to look at a shorter frequency interval, you might say plus 6 dB per octave. Now we need to know, where does that go, or where do we pin it? It's now this sloping line. We have to pin it somewhere on our Bode plot. And we pin it by saying it passes through, let's say 0 dB, where? At omega equal, if you looked at 20 log of omega, that's what this 0 is representing, 20 log of omega, and we're plotting with respect to log of omega, so it's changing 20 dB for every decade, but when omega is equal to 1, log of 1 is 0, it's passing through 0 dB at omega equal to 1. That's what I'm trying to communicate by this sentence after the magnitude associated with the 0 at the origin. What's the phase? That's 90 degrees for all frequencies. And that was, well, if we remind ourselves, we were saying that's 20 times the log base 10 of j omega. J has a magnitude of 1, so this is now 20 times the log of omega. And if we look at 20 times the log of omega when omega is equal to 1, that's 0 dB. That's where that was coming from. Question? So now this is our plot in the S-plane with a 0 at the origin. We want to know, in terms of the angle that that makes as we walk up the imaginary axis, no matter where we step in omega, it's always 90 degrees, because our angle is measured with respect to this positive real line. So we measure from here to there, here to there, here to there, and it's always 90 degrees. What about the pole at 0.5? If you were writing this down, how would you do it? Now we do have two pieces, don't we? We have a flat piece, and then we have a sloping piece. And since this is a pole, it's downstairs, we know the slope is minus 20 dB per decade. There's only one pole at minus 0.5. We are 0 dB in our straight line approximation until what frequency? We're going to assume it's flat at 0 dB until we reach that break at 0.5. We're 0 dB until the break at omega equals 0.5 radians per second. After that, it's going to have a slope, and since it's a pole, that's downstairs, it's now sloping minus 20 dB per decade, and I'll just say thereafter, meaning after 0.5 radians per second. And if we simply had to sketch that, that's what it would look like. Here would be 0 dB. This would be omega equals 0.5, and this would be minus 20 dB per decade. Questions on the magnitude? What about the phase? Now you go into your fairy tales, don't you? The phase is Goldilocks. There's 3 frequencies that we keep track of, and that now tells us for a single pole factor, it tells us these 3 limiting conditions: 0, minus 45, and minus 90. Where are we at? Up until what frequency are we an angle of 0? All the way up until we are a decade before the sweet spot, or Goldilocks' best location, which is the break frequency. We're at 45, right at the break, and then we just look at the pieces around that. This is now 0 up until omega equal 0.1 times 0.5, and we're minus 90 thereafter, 10 times 0.5, or beyond 5 radians per second. And we're straight, we're sloping at 45 degrees per decade negative between 0.05 and 5. Quadratic factor. Now we said this is what we're approximating. To just be s plus 10 squared. Or, in time constant form, we've now written that as the quantity s over 10 plus 1 squared. Again, we can think about its magnitude. It's 0 dB until a break. Where do we break? At the break frequency, which is 10. After that, it slopes up or down? Down, because it's a pole. And how much are we sloping? 20 times 2, or 40, right? So we're minus 40 because this is a quadratic factor. So this is now sloping at minus 40 dB per decade after the break. What's the phase look like? Well, now again, you could write down these three amounts, but we now know that since it's a quadratic, it's going to go from 0 to minus 180 because it's two poles. It's going to be at 0 at what frequency? A decade before the break, which is 1. It's going to be at minus 90 right at the break, which is 10. And a decade beyond 10, or at 100, it'll be minus 180, and it'll be that value from there on after. So that if you were sketching the phase curve for this quadratic term, it would now be 0, and then it would be minus 180. And between those, it's a straight line, so that this is now minus 90 right at the break. Questions on that? Now we would just add all of those up. Do you want to see that? If we look at the magnitude, let's say here's 10 to the minus 2, 10 to the minus 1, 10 to the 0, 100. The constant, let's say this is now minus 6 dB. That's quite far down, isn't it? Well, anyway, I was getting it out of the numbers. So 20 is pretty far down. What's the 0 at the origin look like? Ooh, maybe I should change that. Can I change that and make it a little closer to 0? Okay, I won't. There's 0 dB. Here is going to be 20 dB minus, and here would be plus 20. Now, what's the 0 at the origin going to do? The constant we've already done. That's this, isn't it? This is our constant. It's at minus 6 dB. Now I want to plot the magnitude due to the 0 at the origin. So it's going to go through 0 dB at 1, and then it will be all the way up to 20 a decade after, and it'll be all the way down to minus 20. So this constant, I'm sorry, this 0 at the origin, was I falling asleep again? So this is now the 0 at the origin. Its magnitude. And what else do we have? We have a pole at 0.5. What's the log of 5? Is it 0.6 or 0.7, I think? I think it's about 70%. So it would, here's 0.5, and we now know we're sloping, and if this is now 5, we are sloping this much due to the pole at 0.5, and our other pole is a double pole at 10, so it's going to be right here. And now it won't be at 20, it will actually be at minus 40 a decade later. So it's sloping much quicker. I don't know why I switched colors. Now what do? We add all of those up point for point. Meaning instead of being at minus 20 dB at 0.1, where are we actually at? What's actually in effect at 0.1? The constant and this 0. We have minus 6 and minus 20, so we're at minus 26 at 0.1. So we are right here using my, and the 0 is always sloping, which means that we are always 6 dB below that slope due to the 0. And we just keep coming up until when? Until we reach the first new thing that's breaking, and that's going to be at 0.5. Once we get to 0.5, then the slope due to the pole at 0.5 cancels the slope of our 0 at the origin, and now we're flat. We're now flat, not sloping until we see another break. And that additional break is coming at 10, and then what happens? Now we need to be parallel in slope to that blue dashed line, because that's the only net change in slope, because we've canceled all of our slopes up until that point. Meaning I now need to make my total slope parallel to, so this is now minus 40 dB per decade, and these kinks are happening at 0.5 and 10. And this slope is plus 20 dB per decade, which was this slope right here. Questions on that? This is now the total magnitude of H. What's the phase look like? Are there questions on that? And how we arrived at that? Now we have 10 to the minus 2. Ideally, these would be aligned with the ones up above. They probably are not. We are starting. The constant gives us 0. The pole at the origin, the 0 at the origin gives us plus 90 degrees. This is the 0 at the origin. Where should we end up in phase at high frequencies? Where do we start at low frequencies? What's our phase at low frequencies? The only thing playing or active at low frequencies is that 0 at the origin, right? All the others, the poles, are not starting until 0.05. So low frequencies is below 0.05. And we'll be at plus 90 degrees at low frequencies. At high frequencies, where will we end up? The zero at the origin and one of those pole factors cancel, and we're left with two pole factors giving us phase, so 2 times minus 90. We should end up at minus 90 at high frequencies. I'm sorry, minus 180. 2 times minus 90 is minus 180. It's a new math. 2 times minus 90, we should end up at minus 180. Here's our zero at the origin. We have a phase change due to, here is 0.5, and that will then be contributing phase over a 2-decade interval or span, and it would be this. There's the pole change, or the change in phase due to the single pole, linear pole at 0.5. We also have a quadratic pole at 10, and that will then kick in a decade before and kick off slope a decade after, so that it now is sloping twice as fast as the slope between 0.05 and 5. And now we need to add all of those pieces up. Meaning we're starting up here. That's the only thing in play. If I said, oh, what's contributing phase at that frequency that I've highlighted in yellow? It's only the zero at the origin. We move along until we start seeing slope contributions. And that happens right here at 0.05. Now what happens? Now it goes down parallel to that slope of minus 45 degrees per decade until we reach another kink, and that will occur at 1 before the other one kicks off. Meaning, if we do that, I'm now going down to 45 degrees right there. There's 45. And I hit that dot just right. And I keep that same slope until I reach that point. And then what's my slope? It's minus 45 and minus 90. So now I'm sloping at minus 135 degrees per decade. Which means it's a mess. But I can draw that until I reach right here at 5, and then I will back off and be sloping at what? Only that due to the pole, or the double pole, at 10. So I'm actually going to be sloping very fast until there, and then I'll slow down with my slope, because that's the only thing sloping, and I end up at minus 180. Here I'm sloping at minus 45 degrees per decade. Here I'm sloping at minus 135 per decade, and after this point, right there, I'm sloping at minus 90 per decade. And this is now minus 180 degrees. Questions on that? The blue curve is now my total curve. It's still 828. Do we want to see a convolution? Yeah, no. Well, if you need to leave, I won't be too hurt. I do have some tissues so I can dry my tears as you're leaving. But let's look at a convolution sort of in pieces. Suppose that we have an x of t that is going between -3 and 2, and I did that to make my slope clean, maybe. What's the equation functionally for this? I change 5 in height over a run of 5, so my slope is 1. So this is now t, and my y-intercept is -3. This is now my functional expression for x of t. Suppose that my transfer, or my impulse response, h of t, and this is a hypothetical. Now I'm going to be switching on at 2 and turning off at 5 at 4, or with an amplitude of 4. What does that h of t represent? If that's really the impulse response, what does that say? If I hit this system with an impulse at 0, will I see an output immediately? No, I have to wait 2 seconds, and then it'll start. I'll see it at 4 until 5, and then it'll be done. And that's what happens with an impulse. Can you sort of tell me fairly quickly when y of t is not going to be 0? So now, when am I starting to excite this? If x is my excitation, that's my input, and h is my response, I start applying an input at 0, don't I? But we just said if I hit this with an impulse at 0, I'm not seeing anything until 2 units of time later. So now if I start shaking this with x at 0, the soonest I'm going to see it is at 2, isn't it? So that's my lower limit on when y of t is not equal to 0. It's going to be not moving until t gets bigger or is equal to 2. But now, when is it going to quit shaking? If I hit this at 0 with an impulse, it stops shaking at 5. So now if I start, what's x doing? When does it stop shaking? At 5. This is maybe a bad example, but it takes how much longer to respond to that shake at x equal to 5? 5 more. So now I am going to quit shaking at the sum of those two, isn't it? So y? No, yes, y is h of t convolved with x of t. I'm sorry, it's getting late. It's 8:28. So this is going to be 10. So here's the explanation, or here's one way of thinking of that. H of t tells me the impulse response. That says that if I hit it with an impulse, where an impulse is just instantly on at 0, and then it's no longer happening, then I have to wait 2 units of time before I see anything. It moves at 4, constant, until from 2 to 5. So I hit it at 0, and I kept seeing something at 5. Now, with x of t, I'm still hitting it at 5. Well, I've learned that it still keeps shaking 5 units thereafter. So 5 plus 5 gives me 10. And you could do this by sliding this through if this didn't look right, but another way of thinking of that is you really just add the left endpoints. X is 0, h is 2. That gives you this. And you say, oh, it stops shaking it at 5, and this one quits shaking 5 units thereafter. 5 plus 5 gives me 10. Now, that's assuming that you're always shaking, and I think I gave you on an exam where you had sort of this empty space where it quit. Here, x is always, once it starts, it keeps shaking until it quits. What if you needed to flip and slide one of these? Which would you choose to flip and slide? H of t. You're learning, aren't you? Why? Because h of t is much simpler. That's just a constant. That's easier to think about functionally. Pardon? Sure, that can be on the, you could say that on your notes. You could say, I choose to flip and slide h. And I'll go like this when I'm grading. Any other questions? So let's flip and slide h. We want h of minus lambda. Now lambda is our independent variable. What does that look like? If this is h of t, what's h of minus lambda? Now we just rotate it around the vertical axis at lambda equals 0. We know what h of lambda is. That's just h of t, except with t replaced with lambda. This now looks like that. There's h of minus lambda with a value of 4. If we now want h of t minus lambda, now what do we have? We have the same rectangle, it's just now we have labeled those endpoints slightly differently. Now, when do we have no overlap between h of t minus lambda and x of t? If I'm now, t is a variable that I move from minus infinity all the way up to plus infinity, and that's what allows me to slide h of t minus lambda through x of lambda. As long as t minus 2 stays to the left of 0, so we have y of t equaling 0 as long as t minus 2 is less than 0, or when t is less than 2. And that agrees with our original when is y not equal to 0. What about our overlaps? Well, we know we better start overlapping when we move beyond t equal 2. If we look at this, we now have, here is our axis, there's lambda. We have there's x of lambda, which is lambda minus 3, functionally. We now have slid this guy, t minus 2, and this guy, t minus 5, right there. So that this one has an interval of support there, and the x has an interval of support here. And we want this pattern, or when does this pattern occur? So this is our first overlap. Maybe it's not clear to see, but we can say, oh, t minus 2 needed to be bigger than 0. Let's say now we're doing the equality. That edge needed to move through 0. Maybe we can't see it and we say, well, t minus 5 needs to be less than or equal to 0. And we say, well, I don't know, t minus 2 needs to be less than 5 also. And now you need to make sure which of these happens first. This piece says that t is greater than or equal to 2. That seems okay. This says t is less than or equal to 5. What's this one? t is less than or equal to 7. Whoops, that one can't occur before this other one. So these two that I haven't crossed out must be the ones that are active for this overlap pattern. We need t minus 5 to stay less than 0, and that's going to move through 0 before t minus 2 slides beyond 5. And that's clear if you look at it. H is just 3 wide, and how wide is x? 5. So we're going to have H completely overlapping X in one of these overlap patterns. And I could just ask you for the convolution integral and maybe not have you evaluate it. Although this one you should be able to evaluate, but what's y of t? First, it's an integral, and what you could say is, oh, I have 4, which is my h, and I have my x, which was lambda minus 3, d lambda, and what are my limits of integration? 0 to t minus 2. That's where the red hatching and the blue hatching is overlapping. So I'm now going from 0 to t minus 2, and that's valid as long as t is between 0 and 5. What's the total overlap? That's now going to be beyond 5 and when something else happens, so that we now have this is our x. We now have h. So that this occurs when t minus 5 goes bigger than 0 and t minus 2 is less than 5. Is that right? So that now this is going to occur when t is between 5 and 7. And what's y of t now? It's 4 times lambda minus 3 d lambda. And what are my limits of integration? T minus 5 to t minus 2. And where's my next overlap? A partial overlap. Now we need that right side or that right edge of H to go beyond 5 and the left edge to stay left of 5. We are now looking at this pattern. And this occurs when t minus 2 is greater than or equal to 5 and when t minus 5 is less than 5. Or when we now have t bigger than 7 and less than 10. And what's the integral? Do you see the integrand is not changing? It's still 4 and lambda minus 3 d lambda. And what are my limits of integration? And that's true as long as t is between 7 and 10. And then when do we have no overlap? when t minus 5 gets beyond 5, or when t is bigger than 10, we have y of t equals 0, and that better be consistent with what we derived at the start. So you could verify your work, or that first piece could be a way to check your work. Other questions? Yes. Or questions on this convolution? Not this convolution, you've got another one?
Like the one that practice, I don't know.
All right, I actually printed out the practice final. Ooh, I can't even see the lines. Let me see if I can. So now you have a 1, 0, and this is now 2. Okay, so now what this is, let's say, problem 15 on practice final. And it's wanting to know what is the expression for y when t is between two different limits, between 4 and 6. And the waveforms are these, wow, it's kind of a mess, isn't it? Oh, that's 0. So this is now 1, then this is 3, it's 0, then this is 5, and it goes down to -1 out to 8. That's now what we have. And this is x of t, and h of t is now 2 out to 5. If I'm seeing this right. Is that what it was, I hope? This is now h of t. Which one would you flip and slide? H of t. So now if we flip and slide h of t, that now looks like t and t minus 5 with a magnitude of 2. Is that okay? And now what are we doing? We are actually looking for t between 4 and 6. So we could slide this up until t was equal to 4. And, well, maybe we want to do it when it's between 4 and 6, but if t was equal to 4, do you see that we would now be, and this would be a value of 2, we would be right here, this would be 4, and this would be -1. This is now h of 4 minus lambda. And we want to know what's happening when we slide between that point, and let me get the other extreme, 6. So now we're putting it over here to 6, and where's the left end going to be? At 1. So it will be right here at 1. Can I sort of do it this way? Which means that you're now sliding that solid between the solid and the dashed to find your expression. Does that help? And now you would need to know what's going to happen when I have, let me now put it between those. Now let's just, is the overlap pattern going to change? Yes, you're going to have two different overlap patterns, aren't you? You have one where this -1 stays to the left of 0, and you're going to have another overlap pattern when that leftmost point goes through 0. So you can see that you're going to have several different cases. Is that clear or not? If it's not, you could always walk through this whole thing and just do the whole convolution and say, okay, what are my overlap patterns? And then just worry about the overlap patterns where t is between 4 and 6. But t now, or that particular interval, is not just one overlap pattern. That's actually considering multiple overlap patterns.
For T equals 4, then
So now for t equal 4, this, when it's solid, we really aren't worried about that. We're worried about when it goes a little bit to the right of that. Meaning we are wanting to know what's happening when we are here and when we are here. So we have two different overlap patterns, the left red and the right red. And so this is still, you could still treat this as t, this is still t, and this is t minus 5, and this is t minus 5. But you want to consider this overlap pattern and this overlap pattern to try to find the expression that you need. So if you just had, I wish I had that on the screen, but if you look at option B and option D, those are saying it's the same functional expression between 4 and 6, and you probably are not going to have the same functional expression. So you can sort of process of elimination get rid of those. And then you can try to find what it is based on these two overlap patterns. Okay? Other questions? That was kind of a hurried explanation, but you could work your way through that entire convolution if that wasn't making sense. And once you've done that, you start to see some of these, oh, I wouldn't have had to even consider that up until beyond t greater than 4.
in the exam, how much
Well, what you may want to do, the question was during the exam, how long is it going to take me? It could take you 2 hours. That's the maximum, because the final is only 2 hours in length. And it could take you maybe 10 minutes or 15 minutes for one problem. They're not all equally difficult, the problems. So what I would probably do is I would start thinking through like I've just done and say, how can I minimize the amount of work that I need to put into solving this problem? And you can fairly quickly see that maybe D and B are not valid solutions. And then you can say, okay, what's going to happen in these two overlap cases? Other questions? No time has elapsed off the clock until you look at the real clock, and then a lot has elapsed.